Task number 9. Modify the EIGRP neighborships between router 2 and switch 3, okay, across VLAN 2, such that if switch 3 stops receiving EIGRP hellos from router 2, it will wait for approximately 45 seconds until declaring that neighbor dead. So let's just stop right there. What command would we implement and where would we implement it to accomplish the objective in step 9A? That's right, Asif, we're talking about the hold down timer, so that's what we need to modify. So what's the actual command to modify it and where would we implement that command? Yes, it is an interface command, that's true. This one gets people. This one's a little, you have to think sort of opposite the way you would normally think to get this one. So let's go ahead and go back to our topology diagram here, right there. So we're talking about the relationship between these two guys across SVI2. And according to our objective, it says if switch 3 stops receiving from 2, it'll wait 45 seconds. Okay, so that's saying, okay, if these EIGRP hellos stop coming, then switch 3 after 45 seconds will say, okay, my neighbor's gone, delete him. A lot of people would think, okay, well, then what I probably need to do is go on to interface SVI2, interface VLAN 2, and modify my hold time there. Actually, it's just the opposite. You need to go to your neighbor right here, and on his sub-interface, configure the hold time for 45 seconds. You see, the IP EIGRP hold-time command, the interface command, does not affect your own local hold time. What it affects is when you start sending out EIGRP hellos to your neighbor, inside that hello packet is a field for hold time. You say, hey neighbor, if you stop hearing from me within X amount of seconds, you can declare me dead. So when you configure the hold time parameter on your own local interface, what you're affecting is what you're telling your neighbor. You're telling your neighbor how long to wait until you are declared dead. So in order to affect switch 3, we need to go to router 2. And we need to go onto his fast Ethernet 00.2 interface to implement that. Okay, so before we do that, let's see what switch 3 currently believes the hold time is. How long will he wait right now before we change anything? So, question for you. How do I find that out? What command would I implement on here to see what switch 3 believes the hold time currently is for his neighbor, router 2, across that particular VLAN? Well, it's our good old friendly command, show IP EIGRP neighbor. Show IP EIGRP neighbor. And so this is the .41 neighbor, so right here. So right now he says 11 seconds. If I don't hear from him within 11 seconds, then I will declare him dead. So we're going to bump that up quite a bit to 45 seconds. So let's go over here to router 2 now. And get into that sub-interface. IP hold-time EIGRP, and then we put our autonomous system number. And now we put in 45. Okay, let's see how that affected router 3, or switch 3. See, look at that. It's not exact. We typed in 45, but he set it to, and he actually is getting 45 in the incoming hello packets now from router 2. But he said, oh, I'm going to do 43 instead, just to be a little ornery here. Now, the reason why he does that, the designers of Cisco IOS intentionally put a little bit of jitter in these numbers. In other words, they say, well, we're not going to make them all exactly the same, because if they were all exactly the same, if something happened, we might end up timing out all of our neighbors at the same time. And we'd like to have that staggered a little bit. So that's why it changed the number here. So in order to actually get 45, we'd probably have to play around with it on router 2, maybe set to 47 or 49 or something, but we basically met the objective. The objective was to see if you remembered what the command was and where to implement the command to accomplish a change on your neighbor. So we've done that. Now we're going to do 9b. If router 2 stops receiving EIGRP hellos from switch 3, it will wait approximately 1 minute until declaring that neighbor dead. So now we know, instead of doing the command on router 2, we need to go to his neighbor who's advertising the hellos, switch 3, and change it over there. So let's go ahead and go to, oh, we were already there. And this is going to be on interface VLAN 2, my layer 3 interface of the switch. IP, hold dash time, EIGRP 100, and we want to set to 1 minute, so it's going to be 60. All right, now let's verify that R2 has learned that. And dot 42, here it is. And yep, pretty close, 59 seconds. We could also do this. Oh, I thought there was a way that you could zoom in on a particular neighbor. But you can do it on an interface, fast Ethernet 0/0.2. Yeah, so if you've got tons of neighbors, you could instead just select the specific interface where the neighbor lives. 58 seconds. Interesting. It said 59 before. It's decrementing. That's what's going on here. This is saying, okay, so in reality it probably is 60 seconds. So what we're seeing here is when you receive an EIGRP hello, you reset your hold time back to the maximum and then you start counting it down. Yeah, see, so now it's back up to 59 again. So it probably well and truly is 60 seconds what we're being advertised, and it's just counting down. And EIGRP on LAN interfaces sends out hello packets roughly every 5 seconds or so. So it won't get down too far before it goes back to 60. All right, so that meets the objectives of task 9A and B. Let's take a look at task 10. Modify EIGRP on whichever devices necessary so that router 4 prefers only the PPP over Ethernet connection to R2 to reach IPv4, IPv6 subnet C. And it says you may not disable any interfaces to accomplish this task. Now there's more than one way to do this. Why don't you type into the live question feed, how would you do this? Well, somebody says modify cost. EIGRP does not use cost. If we were talking about OSPF, we could do that. Someone wants to see the command we just did real quick. That's the command we did for the previous task. Okay, well let's look at our topology diagram and then work through this. Okay, so at present router 4, we're talking about this network right here, network C. He's learned about that via an EIGRP update from switch 3, and he's also learned about that via an EIGRP update over the PPP over Ethernet connection from router 2. So first of all, let's go into his routing table and see which one he's preferring right now. So we're talking about the 9.40 network. Okay, so he says, I've only learned about it from one neighbor, which is 9.49, out fast Ethernet 00. So at the moment, he's only got one route in his routing table for that. See, there it is right there. Fast Ethernet 00. Now if we check his topology table, just to make sure that he actually has learned it over the PPP over Ethernet connection, and we can zoom in just on this particular entry, so we don't have to see all of them. And yep, we see two of them. So it says, feasible distance is 28,000 something, 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 and that matches up with this one right here. So that's the best route. And here's another one that's, whoa, look at that, 2,588,000. That is definitely a lot worse than the first one. So what we need to do is somehow make router 4 believe that this route here that I've highlighted is actually better than this route right here. So we could take two different approaches. We could try to do something to make the PPP over Ethernet path look faster than it really is, so that it will lower this number. Or we could do just the opposite. We could do something to make this path here look worse than it really is, something that really bumps this number up by a lot, so it's bigger than this number. So, yep, and Ian's got the right idea. When we want to modify this kind of stuff at the CCNA level, they want you to learn how to modify bandwidth and delay, right? Because they want you to know that bandwidth and delay are the two primary factors that go into making up these distance numbers. And you can modify either or both, but it's recommended not to touch the bandwidth because, like we said, lots of other features also use that bandwidth number to do their thing. Whereas delay, not a lot of other things really look at the delay. So let's try to change the bandwidth. So let's go back to our diagram here. I'm sorry, let's try to change the delay. So looking at this, where would you recommend changing the delay? And you know, so tell me, say, oh, I'd bump up the delay on fast Ethernet 01, or I'd reduce the delay on serial 1/0. Give me an interface and tell me what you would do to the delay on that interface in order to accomplish this objective. Remember, what we're trying to do here is have router 4 prefer this path to get to network C. Okay, well, let's see here. When switch 3, so as far as the bandwidth along this path is concerned, let me change my color here. As far as this path is concerned, remember the delay. I keep saying bandwidth. The delay is the sum of the delays. So for that path, router 4 is considering the delay on this interface, and he's adding it to the delay on this interface to come up with this total delay. So let's try doing this. Let's try increasing the delay somewhere so that this blue path, well, let's see here. Let me think about this for a second. If we do that, that's also going to influence his reachability to networks D and G as well, and we might not want him to do that. So let's try taking the opposite approach. To get this way, he's considering the delay on this and this sub-interface right here. Now, if we reduce those delays by a lot, it should make this path more preferable than the blue path. It will probably also influence some other networks as well. I don't think there's any way around this of just influencing network C. I think anything we do to meet this objective is also going to influence his decisions to reach like networks A and B and D and G as well. So anything about those? So, all right, let's take the red approach. Let's try to decrease the delay. Let's start by just the sub-interface right here. What happens if we go that sub-interface and decrease the delay to the absolute minimum it could possibly be? Let's see if we do that, if that alone will be enough. Okay, so fast Ethernet 00.2 on router 2. So let's go over there. Okay, so before I do that, I'm going to take a snapshot of this. Show IP EIGRP topology. And we're going to be looking for 9.40. Okay, so let me take a quick image of this so we can compare it after we make our change. All right, so we'll keep this up here. All right, so let's go over here to router 2. Interface fast Ethernet 00.2. Delay, and what's the minimum I can do? How about 1? Okay. Let's go back to router 4. Okay. Let's do the same command we did before right here. So we're looking at 9.40. Okay, so before I made the change, on the virtual access interface, that's the interface for PPP over Ethernet, our total delay was 25 or 2,588,000. Didn't change it by much, did it? It knocked it down from 588,000 to 585,000. Not nearly enough for us to get down to something that beats 28,000. So we've knocked that sub-interface down as low as we possibly can. So let's go ahead, and the only other thing we can do at this point is to go on router 4's fast, actually it wouldn't be as fast Ethernet. I believe it would be the delay on his virtual template interface, and knock that down to the minimum. Personally, I don't think that's going to be enough. Show IP EIGRP neighbor. The reason I'm doing this is to determine, so this is the virtual access interface, but you can't really change these. These are like spawned and die, and they come and they go dynamically, and you can't really mess around with them too much. But it's the interface virtual template that actually controls them. And let's knock that down to 1. Okay, what did that do for us? Oh, look at that. That worked. See? Now our virtual access interface is the preferred interface to get to that network. Show IP route EIGRP. And there we go. Now to get to the 9.40, which is subnet C, we're now preferring the PPP over Ethernet connection. So it worked. Also worked on a couple other ones, like here, 9.52. What is that? That's subnet G. So now we're preferring the PPP over Ethernet to get to that. And actually, if you look at the topology, wow, okay, so this subnet right here, he's now taking this way. Down, around, and then down. So yeah, we've given him a different path for subnet C, but now to get to subnet G, not that great. But hey, we don't care about that because the lab objectives didn't say anything about other subnets. So as far as I'm concerned, this is a win. So we have now accomplished step 10. Oh, okay, let's see. And somebody wanted to take a quick screenshot of this. So there you go. You can take a screenshot of that. Any other questions? As far as EIGRP, we're done. We've got one more section on Cisco Express forwarding in this section right here, but we're not going to play around or change EIGRP anymore. We've pretty much done everything from a configuration, verification, and monitoring that the CCNA would expect us to be able to do. So do you have any additional questions? And Frank, to answer your question, Frank's wondering, weren't we supposed to change that delay on subinterface .1. We actually don't have a subinterface .1. If I go back to, where is it? Right here. We've only got subinterface .2 and .3 on router 2. We never created a .sub1. So we create a subinterface for VLAN 2 and a subinterface for VLAN 3. And to reach network C, it was more appropriate to do it on .2. On R2, view the layer 3 Ceph table to confirm it's subnet C and subnet E. What is the technical name of that layer 3 Ceph table that they want us to look at? It's not the data plane. It's used by the data plane. The data plane uses this table to figure out where to forward things. Somebody says the MIB, very close, but the MIB is used by SNMP, not by Ceph. Ian, you've got it. It is the FIB table, the forwarding information base. Exactly. The forwarding information base. So that's what we want to look at. And just as a quick review, remember the forwarding information base is basically sort of a copy of the routing table. The routing table's got stuff that we use to forward packets, but also has a lot of stuff that we don't need to forward packets. For example, to forward a packet between interfaces, we don't really care how it was learned, whether via EIGRP or OSPF or connected, could care less. To forward a packet between interfaces, we don't care what the distance or the cost is. Well, all that stuff is in the routing table. The Ceph table says, the FIB table says, okay, let's just take the bare bones stuff out of there, like the route, the mask, the next hop interface, and the next hop IP address, just that bare bones stuff, and put that in a separate table called the FIB table. And then we can use that table for very, very quick lookups without even having to necessarily interrupt the CPU to go into the routing table and look up the same thing. Okay, so on R2, view the layer 3 Ceph table. So what is the command I want to enter to view the FIB table so I can accomplish this? Well, let's try a couple commands out here. We're talking about R2 and we're talking about subnet C and E. What we want is show IP. Show IP Ceph will do it. There's actually more than one way to get the answer for this, but show IP Ceph definitely will. And we're being told to look for subnet C and E, and on my table here, C is 9.40, and there it is. There's the information for it. And E is 9.48, and that's right there. So show IP Ceph shows us the contents of the forwarding information base, the FIB. It also asks us just to look at this and see if we can recognize any differences and what those differences are. So the first thing is, notice that if you're looking at the topology diagram so we're doing this on router 2. So on router 2, 9.40 is directly attached to him, whereas subnet E, 9.48 is not. He's not directly connected to that. And so in the FIB table, if we look at the differences between 9.40 and 9.48, 9.40 says attached. That means I'm connected to that subnet, and here's the interface I use to reach it. Whereas 9.48, it says, okay, this is the next hop I would use, which in this case is switch 3, and here's the interface I would use to get to that. So that's the difference between attached and a next hop. What do you think this means? Receive. What's that telling us? So if a packet comes in and it matches this, it says receive it. What are we going to do there? That means send it to my CPU. Send it to my CPU for processing. And if we actually take a look at this, 9.47, well, that's not showing up on that diagram. Let's look at another one. How about 9.48? 40, 40. Okay, this is kind of weird. Look at this, 9.44/32. Well, if you look at the topology diagram, 9.44 is actually the subnet address of subnet D, 9.44. So what's that Ceph entry telling us? That's saying if I ever get a packet, and I would never expect to see this, but if some way I get a packet and the destination address, all 32 bits of the destination address are actually destined for the network, send it to my CPU for processing. I wouldn't expect to see that. You would never see a packet destined for the actual network address itself, but we have an entry for it. And similarly, if you take a look at this network, 9.44, well, his actual host address on .3 is 9.45. And here it is. That's his own host address, so that says receive it. That means someone's trying to talk to me. And 9.46 is switch 3's address. He says, I'm attached to that. And 9.47, that is the broadcast address. And so if he gets a broadcast, receive it. So receive means I'm going to send it to myself. I'm going to process it locally, my CPU. So that accomplishes step 11. Step 12. On R2, issue a Ceph-related command to see which exact path R2 would select to transmit packets with these characteristics. So if R2 was creating a packet with his own loopback 0 as a source, and it was going to R3's loopback 2. Okay, well, first of all, let's see, how would R2 even reach loopback 2 in the first place? If we go back to here, so R2 to reach R3's loopback 2, so that is the 333 network. All right, so let's go into R2 again. Show IP route 3.3.3.1. That's the actual address. How would you get there, R2? And R2 says, well, this is the best route that I have, and I would go out fast Ethernet 0/2 to get there. Let's choose a route where he's got more than one path. There's got to be at least one in here. All right, let's see. All these have got just a single entry. Wow. Interesting. So let's see here. Show IP route. Let's do show IP EIGRP topology. Okay, so he has learned about many of those routes via subinterface 3, which is VLAN 3. But for some reason, oh, I know why. Because we went into .2 and we lowered his delay, right? And so that's affecting him as well. He now believes that .2 has a much less delay than .3, and that's why he's preferring .2 for everything. So let's, just for the purposes of doing this test right here, let's change that. Interface fast Ethernet 00.2, do show run interface fast Ethernet 00.2, and let's get rid of this delay here. Set it back to the default. Show IP route EIGRP. All right, that's better. So now, with this particular path, he could choose either VLAN 2 or VLAN 3. And so the question is asking us, if this router actually create a packet himself, for example, if I did a ping, 3.3.3.1, and I use the source of loopback 0. Ping works, but which interface did it take? How do we know? Because he's got two potential paths. Well, by utilizing ceph and a show command, we can figure it out. So that's what's asking us. And you tell me, what show command would I use to figure out, when I just did that ping, which of these paths he took? Did he take 00.2 or 00.3? What's the command to see the answer to that question? The command we're looking for is show IP ceph exact-route. Exact-route. And now you type in here the source address of the session. Okay, so loopback 0 would be 190.198.1. That's what he's using on his loopback. And then the destination. And I can just copy that right here. And it tells me it would go out fast Ethernet 00.3. Second part, what if he used loopback 1 as his source, going to that exact same destination? Well, let's see here. Loopback 1 is the 9.1 address. In this particular case, that would go out the exact same interface. What if you got some random packet? Maybe he's not generating himself. What if it came from some totally different network? Let's just make something up. How about it came from the 777 host? That would also go out .3. So I'm not sure under what criteria he would choose .2. Actually, we can do show IP ceph, and I think we can type in here the network address, 3.3.3.0. Yeah, it's just telling us that. So, not sure what would need to happen for him to send it out this, but the point is for you to know this command right here, show IP ceph exact-route. Really useful command. You just type in the source address of the packet, destination address of the packet, and it will tell you which particular interface it's going to choose. So when you've got equal cost routes and you're not sure which interface it's going to use, easy way to answer that question. All right, so that concludes this section on EIGRP and ceph. All right, so in this video, we're going to be adding a little bit, just a tiny little different element to our network, which is the network time protocol. So at this point, in order to do this section, in order to complete it, all of your IP addressing has to be complete and EIGRP has to be functional. You have to have end-to-end connectivity between all devices. Otherwise, you will not be able to successfully